phasors and AC steady state. Last term, in ELEC 201, we mastered the solution of circuits in DC steady state, a circuit where all sources are constant, and when no switch has been opened or closed in a long time, the circuit is in DC steady state. In DC steady state, all voltages in the circuit and all currents in every element in the circuit are constant. This term, in ELEC 202, we begin with circuits in AC steady state, alternating current, when all the sources in a circuit are sinusoidal functions of time with the same frequency, and no switch been touched for a long time, the circuit is in AC steady state. In AC steady state, all voltages and all currents in the circuit are sinusoidal functions of time of the same frequency. What frequency is that? The frequency of the sources, of course. Tutorial time. In this circuit, we are told all switches have been as shown for a long time. Well, there is only one switch on the right here, and it's closed. They're telling us the circuit is in steady state. Now we look at the sources to find out if it's in DC steady state or in AC steady state. The source on the left is a V source with a sinusoidal value. Peak value 9, frequency 100 radians per second, and phase 15 degrees. The units are volts. There's an anomaly here. You see, the frequency is given in radians per second multiplied times t, which is in seconds. That's radians. How can I add radians to 15 degrees and then take a cosine? Well, that doesn't make sense mathematically. Of course, we need to turn 15 into radians before we apply the cosine function, but it's common practice in engineering to write functions of time that are sinusoidal that way. And the function on the right is another sinusoid. It is a 12 volts peak value cosine of 100 radians per second times t minus 45 degrees. Those are volts. Now we know the circuit is in AC steady state because the sources are sinusoidal with the same frequency, 100 radians per second. We are in AC steady state. What is the conclusion? The conclusion is that this current, that current, this other, and this other one, all of them are sinusoidal functions of time with a frequency of 100 radians per second. We have no idea what the peak value of each one of them is or what the phase of each one of them is. Let's proceed. Assume we give them names IA, IB, IC, and ID. And we're given values for them. The first one, IA, has a peak value of 3 amperes and a phase of 37 degrees. The second one and the third one. Different peak values, different phases. The one thing they have in common is the frequency, same as the sources, 100 radians per second. The question is, who is ID? How do I find it? KCL at the top node. This way, ID is IA plus IB minus IC. If these were constant numbers, that would be a piece of cake. But with sinusoidal functions of time, that can be laborious, right? We need a way to add and to subtract sinusoids, because we need to use KCL with sinusoidal currents and KVL with sinusoidal voltages. We need to be able to add and to subtract sinusoidal functions of time, and to do that quickly, efficiently, and accurately. Who can help us with that? No other than the father of electrical engineering. Who? Charles Proteus Steinmetz. Steinmetz who? This fellow. That short fellow there in the center was a genius of engineering who changed the history of the technology. Standing on his right is Albert Einstein in a picture that was taken 4 years before Steinmetz passed away. So Charles Proteus Steinmetz thinks of it this way. We have two sinusoidal currents, this one and that one, that we need to add. The first one has a peak value A and a phase alpha. The second one has a peak value B and a phase beta. We can represent the first one as a real part of a complex number. What complex number? This one. Check it out. A multiplied by the Euler's number, and the second one can also be represented as a real part of this complex number. Now we know that the circuit is an AC steady state, which means that the sum of those two currents must also be another sinusoid with the same frequency omega, a different peak value c that we do not know, and a different phase gamma that we don't know either. But one thing that is known is that we can also represent that resulting current as a real part of an unknown complex number, like so. Let's write that as an equation on the next slide. We know that the sum must be a third sinusoid with the same frequency omega, an unknown peak value c, and an unknown phase angle gamma. That can be as an equation of real parts of complex numbers this way. But we have learned that adding the real parts of two complex numbers is the same as taking the real part of the sum of those two complex numbers. That equation does not imply this new one. But if the new one is true, the equation that we wrote before is also true. So let's go for that. How do we make this new equation true? We factor out the exponential of j omega t, cancel those time-dependent exponentials, and we are left with an equation with complex numbers. We represent the first sinusoid with this complex number, a, with an angle of alpha, the second sinusoid with its other complex number, b, with an angle of beta. We add them up, we obtain this complex number, which is the representation of the sum, and from there we obtain what is the peak value of the sum and what is the phase shift of that sum. So that is a plan to represent a sinusoidal function of time with a complex number. And guess what Steinmetz called that complex number? He called that a phasor. That's right. So, phasors, a complex number representation of a sinusoidal function of time. This is the function of time. This is the phasor that represents that function of time. What is the plan? The plan is that if we have two sinusoidal currents or two sinusoidal voltages that we need to add or subtract, we represent them with phasors like so. We add or subtract those phasors, and once we have the phasor of the result, we convert that to a function of time. That is how we're going to add or subtract sinusoidal functions of time, currents or voltages. Tutorial time. Let's go back to the same circuit we had before. We were given three sinusoidal currents, we were given an equation, and we need to find the fourth current. Let's do that with phasors. First, let me represent the three currents IA, IB, and IC with phasors. The first one, peak value 3, phase 37. This is the phasor that represents that current. Observe that I represent phasors with an uppercase letter with a little hat. In there, we have the peak value 3 and the phase 37 degrees. What about the frequency? The frequency is the same in the whole circuit. We do not need to represent it anywhere, right? Now, the phasor for the current IB and for IC. Let's do the math on the calculator. Define IA, colon equal 3 with 37 degrees. Enter. Do you really want to create a variable named IA? Yes. Good. Hey, it didn't change my complex number into rectangular representation. Why? Because I am not in CAS. I am in calculator mode, and the calculator mode of the HP Prime is pretty savvy when it comes to dealing with complex numbers. And then I define IB and IC in equivalent ways, similar ways. And now we write ID colon equal, it's defined as IA plus IB minus IC. Enter. That is ID, or rather, that is the phasor that represents ID. The actual current ID with that phasor needs to be written as a function of time. Peak value 2.9 amperes. The frequency is the same, 100 radians per second, and the phase negative 41 degrees. Fine. One question arises very often in the classroom. Hey, what is the meaning of polarities in AC steady state? What? Yeah, those arrows for currents and the plus minus around the V sources, right? Everybody knows that in AC the current is flowing to the right half of the time and to the left half of the time. That in that source on the left, the top is higher than the bottom half of the time, and the top is lower than the bottom half of the time. What's with the arrows and the crosses and minus signs? Oh, what those arrows mean, for instance, the one of IA, is that when the function of time 3 cosine of 100t plus 37 degrees is positive, the current is flowing as the arrow indicates. And what about the plus minus? That signifies that when 9 cosine of 100t plus 15 degrees is positive, the top is higher than the bottom. That's the meaning of polarities in AC steady states. It is a convention. Let's move on with the same tutorial time. What if I were to ask you, what is the current in that resistor? Which one? The one with the current ID in the previous tutorial time, ID sub t. But not as a function of time, but at t equals 0. You say, that's a piece of cake, I know how to do it. Just evaluate ID of t that we found before at t equals 0. Let's do it. ID at 0 is 2.9 cosine of 100 times 0 minus 41 degrees. That is what? That is 2.2 amperes. It is a positive number. That means that that current is flowing according to the arrow in the circuit. It's flowing downwards, and its value is 2.2 amperes. And that is how phasors came to be. You take a sinusoid, you keep the amplitude and the phase. By the way, these are really called peak-valued phasors. Industry uses very often another type of phasor, IEEE phasors, also known as RMS phasors. Those phasors use, instead of the amplitude, the RMS value of the sinusoid. The what? The RMS value of the sinusoid. I will not expand on that concept because that is a topic of a whole nother move. For now, let me just say that for a sinusoid, the RMS value is a peak value divided by square root of 2. That's all. Tutorial time. For the current below, write the peak valued phasor and the IEEE phasor. I of t is 283 amperes cosine 377t plus 36 degrees. The peak valued phasor of that current is, of course, 283 with 36 degrees. And the RMS value? The RMS value is just divide the peak value by root 2. You get 200 amperes with 36 degrees. In a given problem, use only one type of phasor for all currents and all voltages. If you're going to be using peak value, use peak valued phasors for the entire current and voltage set. Word of advice: in a given exercise, choose to work either with sines or with cosines. Don't mix them up. Once you've decided, write all sinusoids in your circuit either as sines or as cosines according to your preferences. Don't mix them up. Choose to work either with peak-valued phasors or with IEEE phasors. Don't mix them up. My preferences? Oh well, I like working with sines myself. Also, I use IEEE phasors mostly because they are standard in the electric power industry. That is why. In practice, sometimes I use peak-valued phasors only if I am asked to write the final resulting voltage or current as a function of time. That is when. When I need to compute power, however, I use IEEE phasors only because the power formulas are simpler when I use IEEE phasors. That is all in what follows. In the rest of the movies of this series, most of the time I shall be using IEEE phasors, but I need to talk more about RMS, and that I shall do in another video. For now, thank you very much for watching, and I hope to meet with you again in the next video.